So we started with the equation that dc is equal to cs ds, and I'm going to, I will not in my various functions write that c is a function of s and t. All of my functions are, of course, functions of s and t. Let's just save notation and not actually express that. So then we have 1/2 the second derivative with respect to s, and then we need a ds squared. And then we have the t derivative of c dt. Okay, so now let's put in ds. What's ds? It's cs is the derivative of c, and ds is alpha minus delta dt, s dt, plus sigma s dz. And then I have to take a half CSS times that expression squared. Alpha minus delta s dt plus sigma s dz. And I'm going to square it. And then I have the ct dt. Now, it's when I square this middle term that I'm going to use the rules that if I have a dt squared, I can throw it away. If I have a dt dz, I can throw those terms away because they have a high exponent of dt greater than 1. The only term out of this square I need to keep in the final formula is the second term squared. And so I get cs. Here I get alpha minus delta s dt. I get plus sigma s dz. And then I get the half CSS, and the only part of that term I need is the sigma squared s squared, and remember dz squared is dt. Here is an example of where those rules of thumb as to how to deal with the dt and the dz differentials when you're multiplying out these various expressions. Again, we know there are those other terms. There is a dt squared term. There's a dt dz term. The point is, in terms of stochastic processes, those terms add nothing because as dt goes to 0, those high powers go to 0 so fast that they have a negligible effect on the process, and therefore we can just throw them away at the start. And all we now have to do is rearrange this algebraically, and we get the second version that we saw here in the box. Okay then. So let's do an example of Ito's lemma, and we'll get an insight on that mysterious minus a half sigma squared term that keeps popping up in the drift of our log normal distributions. So if S is geometric Brownian motion, so my assumption is S is geometric Brownian motion with all the usual parameters. And I want to now look at the distribution of the log of S. Well, log of S is a function of S that I can differentiate. So I can take its first derivative, second derivative. The t derivative is 0. It doesn't depend on t. And when I implement Ito's lemma, it says, here's the process followed by log S. It tells us that log S is arithmetic Brownian motion. And secondly, the drift of the geometric Brownian motion, which was alpha minus delta, has to be further reduced by a half sigma squared. So Ito's lemma provides a very clear and succinct derivation as to why, if S satisfies geometric Brownian motion, why log of S satisfies arithmetic Brownian motion with an adjusted drift term. And the adjustment in the drift term is exactly negative a half sigma squared.